Hi everyone, I want to talk to you briefly today about the electric potential of a point charge. Now, if you remember last week, we defined the electric potential, which is sometimes called the voltage, in this way, as delta V equals minus the integral of E dot dl, where this was along some path. Now, those of you who are remembering your integrals from calculus are saying, right. So whenever you take an integral of something, you could always add an arbitrary constant. And we're going to take advantage of this to set sort of a rule for finite charge distributions. So our rule is we are going to say that we want the electric potential to equal 0 when you are infinitely far away from your charge distribution. So maybe you could even call this the very far away. So what happens is we're going to turn this integral into an absolute electric potential minus E dot dl from some reference to the point that we're interested in finding the potential. Okay? So wherever we are interested in finding that potential, that's sort of the endpoint, and out here is the reference. And for finite charge distributions, that reference is going to be very far away. Okay? So now that we've got the electric potential part of that statement all nailed down, let's think for a second about the point charge part of that statement. One of the things we learned early on was that for a point charge, the electric field was always K, Q over R squared, R hat, where we're centered at the origin and all that business. Okay, so what'll happen if we take this in here? So this is assuming we've got a coordinate system, right? X, Y, with a charge Q at the origin, and at any point, some distance r away, the electric field is pointing out, right? It could be out here, so field is that way, so on and so forth. So instead of thinking about what is the field doing, these field lines going out, right, what we want to start thinking about is what is the electric potential for this sort of thing. And so the integral that we're going to end up setting up is we are going to go say that the voltage a distance r away from this point is going to be minus the integral from infinity. Remember, we said voltage was 0. This is our reference. To r k q over whatever distance r squared dr, and I'm putting primes because this r is the same as this r, and these r's are different. So I'm just indicating that they're different by putting a little prime mark on there. Let's take this integral. So integral k q over r squared dr from infinity to r. kq comes out of the integral. V of r is equal to minus KQ integral dr over r from infinity to r. This integral is just minus 1 over r from infinity to r. This minus sign cancels out, and we are left with is equal to KQ over R minus KQ over infinity, which is, of course, that term is 0. So the voltage due to a single point charge, a distance r away from that point charge, is just KQ over R. And this is going to be the basis for which we make calculations in the future. So if you ever see something like the voltage or electric potential is set to 0 very far away, that's going to be your big hint that this formula applies. So that's going to make you happy because you can use this formula then. In the future, in this week, we're going to use the same. So this week we're going to use the same techniques that we used for the field and the force. But now we're going to be using them with the voltage. So when we had many point charges, we said the total field was always just the field due to the first charge plus the field due to the second charge plus however many charges we have. Well, the total voltage will be the voltage due to the first charge plus the voltage due to the second charge plus however many we have. And if we have extended objects and we have something like a rod that we break, so what we did is we broke it up into a bunch of pieces, said what's the force due to this piece at this point, the field due to this piece at this point, and added up all the pieces. This was either a sum or an integral. We're going to be able to do the same thing for the voltage. And this one will be easier since the voltage has the benefit. Remember, our electric field is a vector and our voltage is a scalar. So we won't have to worry about direction when we do the voltage calculations. All right. Hope you have a good week. We'll see you in class.